What if I told you that the mathematics that make an apple falling from a tree behave properly? Oh, wait, no, let me restart that.
Yeah.
What if I told you the math making an apple fall from a tree is the exact same math causing an artificial intelligence to hallucinate?
I mean, it sounds completely impossible, right? On the surface, gravity and machine learning are just totally fundamentally different universes.
Right, yeah.
Like one is the bedrock of physical reality and the other is just, matrix multiplication inside a silicon chip.
Exactly. But to understand how that bridge even exists, you really have to picture this specific scene. So you're walking into a room, the air smells aggressively like stale coffee and dry erase markers.
Yeah, the classic smell of academia.
Right. And it's 3:55 in the morning. You have exactly 5 minutes before the metaphorical bar closes for the night. And you are staring at a whiteboard that just looks like a beautiful, chaotic disaster.
Yeah.
It's absolutely covered in equations, crossed out diagrams, frantic scribble.
It is like the universal visual representation of an intellectual bender, the kind of scene where you just know someone has been standing there for 8 straight hours, just unraveling the fabric of reality, one marker stroke at a time.
And right in the center of this chaotic whiteboard, circled maybe 3 or 4 times, is this stupidly innocent question. The question that started this entire descent. It just says, what is the mathematics of before and after?
Which honestly sounds like a question a child would ask.
It totally does.
And in theoretical physics or mathematics, a child's question is usually a massive red flag. It means the answer is going to be mathematically terrifying.
Terrifying is definitely the right word here.
Yeah.
Because we have the source material detailing exactly what happened in that room during that all-nighter. And in this deep dive, we're going to trace that exact rabbit hole.
Yeah, we really are.
We're going to go from basic questions about time and causality into cryptography, straight through the science of measurement, into something called a cursed physics problem.
Oh, the cursed problem.
Yeah, we'll get there. And finally, somehow we're going to crash right into the architecture of modern AI transformers.
But, before we take this plunge, we really need to set a ground rule for what this actually is. We aren't just leaping randomly between these completely different fields just to sound smart.
Right, no, not at all.
Every single step in this progression, every strange turn this session took was a forced, logical step based on absolute mathematical necessity. Like, when one paradigm broke down, the math demanded the next one. There is a singular, unbroken thread connecting all of it.
Okay, let's unpack this. Because I can promise you, listening right now, that by the end of this deep dive, your fundamental understanding of time, of artificial intelligence, and of how we measure reality itself is just going to be completely rewired.
Oh, absolutely.
So let's go back to the beginning of the night. The question on the board is, suppose I say event A happened before event B. How do we model that mathematically?
Right. And usually when you ask a physicist or computer scientist how to model A happen before B, everyone immediately reaches for the standard toolkits.
The usual suspects, yeah.
Yeah, they think about causality, temporal logic, the space-time continuum, or directed acyclic graphs, which are essentially just complex flowcharts showing how one thing leads to another.
You just draw an arrow from A to B. It's simple.
Exactly. But the source material notes that there is a much smaller, far more fundamental question hiding underneath all of those concepts.
Wait, really?
Yeah. Before you can even ask how to draw an arrow from A to B, before you can ask if A is less than B, or if A caused B, you need to know something else. How did you know there were 2 separate things to draw an arrow between in the first place?
Hold on, say that again. You're asking how I know A and B are 2 different things.
Exactly. Mathematically, before you can ask if A is strictly less than B, you already needed to establish that A does not equal B.
Oh.
Yeah. The foundational insight here, the absolute bottom floor of reality, is that order presupposes distinction.
Okay, I want to make sure I'm wrapping my head around this. Because my instinct is to say, well, if I have 2 identical red marbles, I can still put one in front of the other. Like, I can order them even if they're the same.
But how do you know you have 2 marbles?
Because I'm holding 2.
Oh.
I see. I can feel one in my left hand and one in my right hand. The spatial location is the distinction.
Precisely. The location makes them distinct. If they occupied the exact same space at the exact same time with the exact same properties, they wouldn't be 2 marbles.
They'd just be 1 marble.
Right. They would be 1 marble. You need the capacity for distinction, the ability to mathematically say A does not equal B before the concept of sequence or order even has any meaning at all.
I really love this. It's kind of like organizing a massive bookshelf. You can have this, brilliantly intricate system for alphabetizing your books, which represents your temporal order.
Yeah.
But if you walk into that library completely blindfolded, wearing thick winter gloves, and you literally cannot tell one book from another, you have lost the capacity to distinguish them, then your alphabetizing system is completely useless. You cannot order what you cannot distinguish.
That is a perfect analogy. You need the mechanism of distinction before causality can exist. So the realization in the room was that causality isn't the bottom floor of physics. Distinction is.
Which sounds incredibly philosophical.
It does. And the source notes that this sounded pleasantly philosophical for a few minutes, but then they made the classic mistake of trying to write down an equation for it.
Of course they did.
They introduced a specific mathematical operation called an idempotent operation.
I've seen the equation in the notes. It's written as the Greek letter pi squared equals pi. So break that down for me. What does that actually mean in plain English?
So an idempotent operation is a mathematical action where applying it once changes the state of something, but applying it again and again and again does absolutely nothing further.
Okay.
The result just stays the same.
I'm going to need a physical example of that.
Think of an elevator call button. You walk into a lobby and the elevator is on the 10th floor. That is your initial state. You press the call button, that is your operation pi.
Right.
The state changes. The elevator is now summoned to the first floor.
Okay, so pi applied to the state changed the reality of the building.
Right. But what happens if you frantically press that same call button 5 more times?
Nothing. I just look impatient.
Yeah.
The elevator's already coming to the first floor.
Exactly. Pressing it once, which is pi, achieves the exact same result as pressing it twice, which is pi squared. So pi squared equals pi. In mathematics, operations like this are used to create a primitive split in reality. They act like a sorting mechanism.
Wait, how does pressing a button split reality?
Because it forces every possible state in the universe into one of 2 categories. Category 1 is the states where applying pi does nothing, because they are already in the final condition. We call these fixed states.
So in the elevator analogy,
this is a universe where the elevator was already waiting on the first floor when you walked in. You press the button, nothing changes. The state is fixed.
got it. And the other category?
Category 2 is the states where applying pi does change something. We call these displaced states. This is the universe where the elevator was on the 10th floor and your action fundamentally altered the system.
So they were using this pi operator to define what distinction actually is at a mathematical level. Distinction is the boundary between the fixed states and the displaced states.
Yes, and according to the source material, trying to map this boundary triggered a massive metaphysical debate. They apparently went down this deep, abstract rabbit hole involving negative space, the concept of the actual self, and the logical not operator.
Yeah, the notes literally say there was an entire metaphysical episode. You were lucky you missed it.
Yeah.
So we were officially skipping the metaphysics of negative space.
Highly recommended to skip it, yeah.
But the useful residue that survived that debate was this idea that a mathematical operation can partition the world based on which distinctions survive the operation. But right as they were settling on that, the whole framework collapsed because someone asked a devastating question.
Distinguishable by whom?
Yes, distinguishable by whom? It's such an irritatingly brilliant question because up until this point, they were acting like distinction is just a God-given objective fact of the universe. A is objectively different from B.
But objective difference doesn't matter if the observer in question lacks the budget to actually see it. And this is where the math leaves pure philosophy and gets deeply, deeply practical.
Okay, lay it on me.
Let's say X and Y really are objectively different things. If I give you, the observer, a finite computational budget, let's call it budget B, it is entirely possible that no experiment you can possibly run under that budget will allow you to tell X and Y apart.
So to me, they are literally the same thing.
Precisely. The notation they use is X tilde BY, meaning X is indistinguishable from Y given budget B.
But wait, if I can't tell them apart, how do I interact with the world? I mean, if I'm trying to do physics or build a system and I can't see the underlying objective reality, what reality am I actually living in?
That is the exact crisis they hit, because you don't operationally live in the objective world. You inhabit a mathematical space called an operational quotient.
Okay, I need us to really dig into this equation because it looks super intimidating on the board. Q sub B equals X over the indistinguishability relation.
Yeah, it looks intense.
What does the over mean physically? It looks like division.
It is a type of division, but not like dividing numbers. It's a spatial division, a quotient space. The X on top is the vast, infinitely detailed objective reality, the universe as it truly is. The tilde on the bottom is your limitation, your finite budget.
So when I divide objective reality by my limitations, what do I actually get?
You get clumps. Think of it this way. Imagine you have a giant pile of thousands of different colored socks. That's X objective reality. Every sock is a slightly different hex code of color.
That sounds like a nightmare to sort.
It is, if you have infinite time and perfect lighting, but your budget B is that you have 10 seconds and the room is dimly lit. What happens?
I just throw all the vaguely dark ones into one pile and all the vaguely light ones into another pile?
Exactly. You have just created a quotient space. You took a complex reality, X, and clumped it together based on what you couldn't tell apart. The dark pile is now a single operational state to you.
Wow.
Inside that pile, there might be a navy blue sock and a black sock that are objectively different. But to you, under budget B, they occupy the exact same operational state.
So the quotient space isn't just a blurry version of reality. It is my reality. It's the only sandbox I get to play in.
What's fascinating here is that as soon as they formalized this idea that reality is dictated by observer limitations, they realized another field of mathematics had already built a multi-trillion-dollar industry on this exact concept.
Cryptography.
Yeah.
The source material has this amazing moment where they personify a famous cryptographic cipher called Cha-Cha-20.
Yeah, it's a great image.
They imagine it sitting in the corner of the room, sipping a drink, and looking at the physicists like they're idiots, saying, "I've been doing this since 2008.
Because cryptography thrives entirely in the gap between objective reality and the operational quotient. Think about how encryption works. When a cipher encrypts your credit card data, does it turn it into a mathematically perfect random sequence of noise?
I mean, I always assumed it did, yeah.
It doesn't. If you had infinite computational power, you could look at the encrypted data, find the subtle patterns, and realize it is objectively not random. It is completely deterministic.
But I don't have infinite computational power. I just have my laptop.
Exactly. The cipher's job isn't to create true randomness. Its job is to create a sequence that you cannot distinguish from true randomness given your computational budget. It is weaponizing that indistinguishability relation.
So if it takes my laptop 10,000 years to find the pattern in the data, then for all operational intents and purposes, under my budget, it is completely random.
Yes. The foundation of modern cybersecurity relies on computational indistinguishability. So the mission of the people in this room completely shifted at this point.
Right.
The question was no longer the philosophical, what exists objectively. The question became deeply pragmatic. What distinctions are operationally realizable at a given resource level?
I really want you listening to this to stop and think about your own physical budget for noticing things. Because we do this every single second.
Oh, constantly.
Think about looking at a forest from the window of a car going 70 miles an hour.
Yeah.
You do not see millions of individual distinct leaves. You don't have the cognitive, visual, or temporal budget to process that geometry in a fraction of a second. What do you see?
You see a green blur.
A green blur.
Yeah.
Your reality is the quotient. You act on the green blur. The distinction between a maple leaf and an oak leaf objectively exists in the universe, but operationally, for you, in that moment, it does not.
Yeah.
The distinctions are literally crushed by your lack of resources.
And that transition, realizing that resources crush distinctions, leads us directly into the next phase of the all-nighter. But to truly map how this crushing happens, they realized they couldn't just talk about generic budgets floating in a void. Observers exist in space. They have geometry.
Which brings us to the decision to turn this into an Iridov problem for absolutely no reason.
Classic.
For those who don't have trauma from physics grad school, Iridov is infamous. He wrote these legendary, brutally difficult Russian physics problem books. So the group decides to make things ridiculously hard for themselves. They imagine placing these resource-bounded observers onto a physical grid, specifically a 25 by 25 lattice.
Let's visualize this carefully. You have a grid. At various intersections on this grid, you have observers. They gave each observer a finite witnessing capacity. Let's call that capacity C sub O, for capacity of the observer.
Think of it like the quality of a telescope you've been given.
Good. Now, any phenomenon happening somewhere else on the grid, say, two objects sitting very close together, requires a certain amount of capacity to be noticed as two distinct objects. Let's call that C sub D for capacity of the distinction.
So the primitive question just becomes an inequality. Is the capacity of the observer greater than or equal to the capacity of the distinction? Does my telescope have enough power to actually witness the gap between those two objects, or do they just blur into one?
Right, but to make this behave like real physics, they added a spatial rule. An observer's capacity to witness something should decay with distance. The farther away an event is from you on the grid, the less capacity you have to witness its fine details.
Which makes perfect physical sense. I mean, gravity decays with distance. Light intensity decays with distance.
Exactly. So they experimented with different mathematical rules for how this resource decays across the grid. They tried continuous smooth functions. They tried gravity-like inverse square laws. They tried exponential decay curves, logarithms.
Just throwing everything at the wall.
Yeah, the source notes that nobody remembers why they tried all of them, just that they were desperately looking for a pattern.
But what matters is what happened when they ran the numbers, because they stumbled onto something that broke their intuition about how physical laws work.
They found that even if the underlying rule for how resources decay is perfectly mathematically smooth, like a beautiful, continuous exponential curve, the fact that the observers were placed on a finite grid produced something entirely non-smooth.
A discrete staircase of reality.
Yes, you have this continuous flowing equation of resources, but operationally, for the observers on the lattice, reality suddenly snaps into discrete levels. You either have the exact budget required to see the next level of detail, or you don't. There's no fuzzy in-between state of sort of seeing it.
I need to grasp why a smooth curve creates a sudden jump.
Think of a digital camera sensor. Light hits the sensor in a perfectly continuous analog wave. The intensity of the light is smooth, but the sensor is a grid of discrete pixels. Each pixel has a threshold. If the light energy is 49% of the threshold, the pixel registers as pitch black. If the light hits 50%, it instantly registers as illuminated.
So the smooth analog wave of light is forced into a binary digitized reality because it hit a threshold on a grid.
Precisely. Going back to our personified cryptography cipher, the source has Cha-Cha-Key chiming in from the corner again, saying, "You gave me a smooth function and a lattice, and I gave you a staircase."
It's a brilliant encapsulation. And this staircase effect forces us to reconsider how we view the universe. We often assume that because the underlying laws of physics are continuous, like the fabric of space-time, our experience or measurement of the universe should also be continuous.
And it isn't.
Right. The fundamental geometry of bounded observation inherently digitizes a smooth reality. The very act of looking with a finite budget chops the universe into stairs.
And speaking of geometry, as soon as they realized this digitization was happening, they started drawing lines on the whiteboard to track it. The observers on the grid started forming a topology.
Okay, we are entering dense mathematical territory here. We really need to build this topology piece by piece for the listener. Let's start with just two observers on this grid, observer I and observer J.
Imagine them standing on this giant checkerboard. If observer I has enough resource budget to successfully witness observer J, meaning their capacity is greater than the distinction required, you draw a line connecting them. Mathematically, that line is called an edge.
Okay, simple enough. I can see you, so we are connected by a string. Now, instead of just isolated points, we have a network, a graph.
Now, what if an entire group of 3 observers can all mutually witness each other?
Okay.
Like I sees J, J sees K, and K sees I. You don't just draw 3 separate strings. You fill in the entire space between them. You create a solid triangle.
Like stretching a tarp between 3 poles.
Yes. In topology, that filled-in triangle is called a 2-simplex. And if you have 4 observers mutually witnessing each other, you build a 3-dimensional tetrahedron, a 3-simplex. As you find larger and larger groups of mutually witnessing observers, you build more complex, higher-dimensional solid shapes.
So depending on how much budget everyone has, you get a highly specific, complex geometric sculpture made out of these filled-in connections across the grid.
They call this a resource-indexed simplicial complex. And the fascinating part is what happens when you start turning the dial on the budget. Imagine a slider on a soundboard that controls budget B.
Okay, I'm sliding it up. I'm giving everyone more budget.
As you slide it up, people can suddenly see further. Edges appear out of nowhere. Separate, isolated clusters of observers suddenly merge into massive, solid structures.
And if I slide the budget down, I'm restricting their resources.
As the budget drops, those solid structures start to decay. Geometric holes literally form in the middle of the network as people lose sight of each other. The whole topology collapses back into isolated points.
Meaning that this operational reality we've been talking about, this quotient space, isn't just a conceptual list of what you can and can't see. It physically possesses a shape. It has a high-dimensional geometry that morphs, breathes, and tears itself apart based entirely on how much resource you have.
And at this point in the night, someone in the room stared at these morphing shapes and apparently pointed out, bro, this is basically Viatorus Rips.
Which sounds like a spell from Harry Potter, but what is it actually?
A Viatorus Rips complex is a highly specific mathematical tool used in topological data analysis. If you have a massive cloud of random data points, you want to know its shape. So you say, connect any 2 points that are within a distance of epsilon.
Right.
As you increase epsilon, the dots connect, triangles fill in, and the hidden shape of the data reveals itself.
Wait, so the physicists in this room started with the philosophical concept of causality, they added a finite observer budget, and mathematically, they independently derived the exact framework used by data scientists to analyze massive data sets.
The source clarifies they weren't claiming to have invented Viatorus Rips complexes at 1 in the morning. The point wasn't the invention, the point was the shock of recognition. Why did this highly specific mathematical grammar keep showing up?
And that shock of recognition hits its absolute peak shortly after when, as the source describes it, metrology walks in and ruins the metaphysics.
We definitely need to define metrology because it's the anchor for this entire realization.
Metrology is simply the scientific study of measurement. It's the science of rulers and scales and clocks and thermometers. It's how we physically quantify reality.
And the devastating realization they had was that measurement devices already do everything they had been theorizing about on this whiteboard.
Because of their limits.
Right. A physical ruler cannot distinguish between 2 lengths if the difference is smaller than the millimeter marks etched onto the wood.
Yeah, if one piece of paper is a millionth of an inch longer than another, but I only have a standard wooden ruler, they are mathematically indistinguishable to me. They occupy the same space in my quotient reality.
A clock cannot resolve the difference between 2 events that happen a microsecond apart if its internal mechanism only ticks every second. Every physical instrument has a bounded resolution.
Every microscope has a maximum magnification before the light diffracts. Every smoke detector requires a threshold density of particles before the alarm triggers.
Measurement itself induces equivalence classes. The physical limits of our tools create our operational quotients.
So this whole time, this wasn't just some abstract thought experiment about computational budgets or data topology. Metrology, the actual physical science of measuring reality in a laboratory, had been living inside this exact mathematical framework all along.
If we pull back and look at the guest list that has now arrived at this whiteboard, it is completely absurd. You have cryptography dealing with computational indistinguishability and exhausting an attacker's budget.
You have metrology dealing with finite resolution and the physical limits of rulers and clocks.
You have control theory dealing with what engineers call observability, which is the mathematical limit of whether you can determine the internal state of a complex machine just by looking at its external outputs.
You have statistical mechanics dealing with coarse graining. The fact that we treat 1 trillion bouncing gas molecules as just temperature and pressure, because tracking every individual atom would require an infinite budget.
And you have topological data analysis dealing with scale index geometry.
It's a ridiculous list.
Yeah.
I mean, you can't unlock your encrypted phone with a thermometer. These are not the same sciences.
They are not the same series, no. But the crucial insight the group had was that all these fields instantiate a common grammar. They all share the exact same underlying skeletal structure.
And what is that structure? Stripped down to its studs.
You start with a state space, the objective universe. You introduce a set of resource-indexed experiments. What tests can you actually run with the energy, time, or tools you possess?
Okay.
That limitation defines what is indistinguishable to you, and that indistinguishability leaves you with your operational quotient, the blurry reality you actually get to interact with.
The source material calls this framework RBDS, Resource-Bounded Distinction Systems. But the sobering core thesis of the entire night crystallized right here. They wrote a single sentence on the board. Observation is a resource.
Observation is not free. It is not a passive magical window into the objective universe. It costs something. It costs computational cycles or physical energy or time. And because it costs something, different resource budgets draw completely different boundaries between what is distinct and what isn't.
And as the notes point out, they really could have stopped here. This is a profound, unifying realization across multiple domains of science. It's elegant. They could have taken a picture of the whiteboard, gone home, and written a brilliant paper about the unifying theory of bounded observation.
But they were mathematically intoxicated, and the bar didn't close for another couple of hours, so they did not stop. Instead, things took a turn for the chaotic. As the source material warns, here is where the party becomes unrecoverable.
Because somebody decided to take this beautiful static geometry of observation and apply it to gravity. They decided to give gravity an attention span.
This is where we enter the territory of the cursed three-body problem.
Okay, we need to set the stage for this carefully. In standard physics, the three-body problem is already famously chaotic. You take three massive objects, like 3 planets or 3 stars, and you calculate how their gravity affects each other as they orbit in space. Because they're all constantly pulling on each other and moving, the math becomes incredibly complex.
Right. It's almost impossible to predict their paths perfectly over long periods, but the primitive force law underneath that chaos is remarkably simple. Gravity acts between every single pair of bodies based on their mass and their distance. Everybody observes and interacts with every other body simultaneously, all the time.
Standard gravity doesn't get to choose who it pulls on.
Exactly. But the group at the whiteboard decides to change the rules of observation based on what they just learned. They say, imagine these 3 bodies, but each body has a limited observation budget. In fact, its budget is so limited that it only interacts with whichever body it currently observes as its farthest neighbor.
Wait, so if planet A is near planet B, but far from planet C, planet A completely ignores planet B.
Yes. Observation is no longer just passively describing the system. Observation creates a state-dependent graph. We use the mathematical notation A equals A of x. The attention matrix, A, changes dynamically depending on the physical state, x, of the bodies.
And that graph becomes a gatekeeper for the physics. Gravity is no longer an automatic universal force. Gravity only flows along the lines of attention. If body 1 is not paying attention to body 2, body 1 feels literally 0 gravitational pull from body 2, even if they are right next to each other.
The physical interaction is explicitly gated by the observational resource, and this leads to a massive fundamental break in standard physics.
Okay, I have to stop you here. I have to push back on this entirely, because my high school physics teacher is screaming in my head right now, Newton's third law.
For every action, there is an equal and opposite reaction.
Yes. Reciprocity. If I pull on you with a force of 10 newtons, you pull on me with a force of 10 newtons. It is the absolute bedrock of physical mechanics. If these planets are suddenly turning off their gravity based on attention, isn't this system just violating Newton's laws and breaking physics entirely? How can this math possibly work?
That is the exact tension that broke open their next massive discovery. Because they didn't break Newton's third law, the underlying physical force law in their equation, the primitive pairwise interaction, remained perfectly reciprocal. If body A and body B do interact, they pull equally on each other.
Hold on, I'm confused. If the physical law is reciprocal, how is the system behaving weirdly?
Because the attention is asymmetric. The selection of who is allowed to interact with whom is not reciprocal.
Okay, I need a map of this. Walk me through the asymmetric attention.
Let's use the matrix notation they wrote down. A sub I does not equal A sub j. This means the attention body I pays to body j is not the same as the attention j pays to I. Let's look at the 3 bodies. Body 2 is looking around, and its farthest neighbor is body 3. So body 2 pays attention to body 3.
Okay, so a gravitational link forms between 2 and 3.
But body 3 is also looking around, and from body 3's perspective, its farthest neighbor is body 1. So body 3 ignores body 2 entirely and pays attention to body 1.
Ah. Body 2 is screaming for body 3's attention, but body 3 is completely focused on body 1. The underlying law of gravity is reciprocal, but the attention mass placed over it is asymmetric.
It creates a directional flow of focus.
It's like a truly terrible group chat for a work project. Let's say you, me, and a third person, let's call her Sarah, are collaborating. We all have the exact same messaging app. That app represents the reciprocal physical law. If I send a text, it arrives instantly. The physics of the app are equal and fair.
But the attention is restricted.
Exactly.
Yeah.
I am heavily anxious, so I am only reading Sarah's texts. Sarah is frustrated, so she is only reading your text, and you are only reading my text.
An asymmetric attention topology.
Yes. The fundamental rules of the messaging app haven't changed. But because of who is paying attention to whom, the entire direction of the project starts drifting completely off course. No one is on the same page, even though the underlying physics of the communication is perfectly reciprocal.
And that drift in your group chat analogy translates mathematically perfectly to the physics equations on that whiteboard. Because of this asymmetric attention, you get effective non-reciprocity. And this non-reciprocity generates what physicists call center of mass motion.
Center of mass motion, meaning the entire system of 3 bodies as a whole starts accelerating and drifting through space in a specific direction.
Yes. Normally, a closed system of interacting bodies cannot spontaneously accelerate itself in one direction. Its total momentum is conserved. If everything pulls equally, it stays put in space. But when you split the attention matrix into a symmetric part and an antisymmetric part, they use the mathematical symbol omega for the antisymmetric part. The balanced interactions cancel out, but the antisymmetric sector survives.
I'm looking at the equation for this drift right now. It says P dot total equals the inner product of omega and j. Break down those variables for me.
P dot total is the change in the total momentum of the system. It's the literal drift. Omega is the antisymmetric part of the imbalance of who is looking at whom. And J is the actual physical interaction, the gravity. The angle brackets mean you take the inner product, you multiply them together.
So the drift is directly generated by the imbalance in attention multiplying the physical force.
Fundamentally, this means the asymmetric attention actually generates macroscopic directional momentum. Not because the primitive force became magical or violated physics, but because who interacts with whom became directional. As the source material states, observation was no longer merely describing dynamics, it was selecting dynamics.
Selecting dynamics.
Yeah.
That is a profound shift in how we think about reality.
Yeah.
By choosing where to spend your observational budget, by choosing what distinctions matter to you, you aren't just measuring reality, you are literally propelling it in a specific direction. You are creating physical drift.
And because they now had a mathematical system that actually produced drift, they wanted a cleaner, simpler way to measure it. They wanted to isolate the exact engine of this movement. Which brings us to the concept of column imbalance.
This part of the math is just so elegant. So we've established that attention is asymmetric. The way they model this structurally is by assuming that every observer gives out exactly one unit of attention. This is called row stochastic attention.
Think of a spreadsheet matrix. Every row represents an observer planet 1, planet 2, planet 3. The values in that row represent who they are paying attention to. The rule of being row stochastic means the sum of every row is exactly 1. Everyone has the exact same total attention budget to spend.
But, and this is the crucial part that creates the chaos, just because everyone spends exactly one unit of attention does not mean everyone receives one unit of attention.
Exactly. While the rows sum to 1, the columns, which represent the attention being received by a specific body, do not necessarily sum to 1. In mathematical terms, A transpose times a vector of 1s does not equal 1.
Well, let's bring this back to reality. If planet 1 is super interesting, planet 2 and planet 3 might both spend their 1 unit of attention on planet 1.
Which means planet 1 receives 2 units of attention. It is an attention sink.
And planet 2 and 3 receive 0. They are attention deserts.
Precisely. So the mathematicians created a single Greek letter to measure this exact discrepancy across the entire system, delta.
Delta. The formula is delta equals A transpose times 1 minus 1.
This delta is the literal measure of column imbalance. It is a precise mathematical map that tells you exactly where attention is accumulating and where it is being depleted across the entire network.
And when they plugged this delta back into their mechanics equations, it perfectly predicted the drift of the planets. The equation became the sum of forces equals G times delta transpose X.
Meaning, delta tells you where the attention imbalance is. And delta transpose X, where X is the physical location of the planets, tells you exactly what happens. It tells you how the physical system will contract and drift through space based entirely on that imbalance.
It's beautifully self-contained. They found the mathematical engine of the drift, delta. And they've just essentially invented a new form of active matter physics based entirely on attention budgets. And this is exactly the moment where things get truly mind-bendingly wild, because this is where artificial intelligence enters the building.
The source material refers to this moment as the transformer incident.
I can picture this vividly. It's deep into the night. One of the people in the room, clearly vibrating on an absurd amount of caffeine, stops looking at the physics equations on the left side of the board and starts drawing the architecture of a modern AI neural network on the right side, specifically a transformer.
For context for the listener, the transformer is the underlying architecture of almost every major AI model today, from ChatGPT to image generators, and the core processing mechanism inside a transformer is called the attention head,
which computes how different pieces of data, like words in a sentence, which the AI calls tokens, should pay attention to each other to understand context. The fundamental equation for transformer head is y equals AV.
Let's unpack that. V stands for the values, the original mathematical representations of the words. A is the attention matrix, determining which words care about which other words, and Y is the new, updated representation of the sentence after the attention is applied.
So this caffeinated person at the whiteboard does something very simple. They look at y equals AV. They sum up all the token representations after the attention mechanism is run. They want to see how the overall meaning of the sentence shifted in the AI's brain. And they realize that the change in the aggregate representation, the literal drift in the AI's understanding of the data, is governed by delta transpose V.
Which is the exact same math they just derived for the three-body physics problem.
Wait, I want to make absolutely sure I'm getting this completely right. They're saying that the formula controlling the physical center of mass drift in this weird, cursed gravity problem is the exact same formula controlling how AI word tokens drift inside a neural network.
Yes. In the physics problem, the aggregate physical drift is controlled by delta transpose X, which is the column imbalance times the physical state. In the AI transformer, the aggregate representation drift is controlled by delta transpose V, which is the column imbalance times the value state.
That is insane.
As the notes describe it, everyone stares at the board. They are not the same physics. They are not the same objects. One is a hypothetical model of celestial planets with selective gravity, and the other is a massive matrix multiplication inside a silicon chip processing human language.
But the algebraic mechanism is absolutely identical.
The mechanism is a structural inevitability. Row normalized local allocation plus column imbalance inevitably leads to aggregate drift.
Let's repeat that translation. Row normalized local allocation, meaning everyone gets exactly 1 unit of attention to spend, whether you are a planet looking at another planet or an AI word token looking for context in a sentence.
Plus column imbalance, meaning some planets or some words receive way more attention than they give. They become sinks.
And that combination must mathematically produce a drift, whether it's physical momentum or semantic hallucination.
Finding this undeniable bridge between active matter physics and neural attention in AI sent the room into overdrive, because now they didn't just have a neat observation, they had a predictive engine. They formed a massive hypothesis.
Right. They start thinking, okay, if this non-normal asymmetric attention causes drift, maybe it creates dramatic cascading amplifications over time. Maybe this imbalance is a chaotic multiplier that causes AI models to completely explode in complexity.
They hypothesized that non-normal attention creates dramatic finite time pseudospectral amplification.
Which sounds like a phrase you would use to try and secure a billion-dollar grant for a particle accelerator. Pseudospectral amplification.
It sounds incredibly dramatic, but they had computers in the room. They ran the simulation to test this dramatic amplification, and the computer basically spat out the answer, no.
Lol, no, according to the source material. The experiment utterly failed.
It failed, but as we often see in theoretical mathematics, a clean, definitive failure is incredibly productive. What they found was that you can have an attention matrix that is strongly non-normal, meaning the attention is flying all over the place asymmetrically, but it exhibits absolutely no global amplification whatsoever.
They tested it with something called doubly stochastic matrices. Explain what that means in contrast to what we had before.
Before, we had row stochastic attention. Everyone gives 1 unit, but reception is imbalanced. A doubly stochastic matrix is perfectly balanced on both sides. Every row sums to 1 unit of attention. Everyone gives 1 unit of attention, A and D. Every column sums to exactly what. Everyone receives exactly 1 unit of attention.
Meaning there are no attention sinks. There are no deserts. Column imbalance is completely eliminated. Delta equals 0.
Exactly. And they found that if delta equals 0, even if the attention is highly asymmetric in who is looking at whom, the system does not blow up. The equation states that the norm of the system stays exactly at 1 for all time.
So the conclusion was, asymmetrical attention alone does not lead to aggregate amplification. The dramatic pseudospectral hypothesis died right there on the whiteboard.
But out of the wreckage of that failed hypothesis, something much, much deeper emerged. The stationary bias theorem.
This is a beautiful piece of mathematical salvage. They realized that the column imbalance, that delta we keep talking about, isn't just correlated with the drift. It is the literal forcing term that creates a permanent baked-in bias in the system.
Let's break down the mechanics of this theorem because it defines how modern AI actually behaves. They introduced a variable called pi. In this context, pi is the stationary distribution of the attention matrix. It represents where the system naturally wants to settle down and rest after a long time.
And they introduce another variable, u, which represents the perfectly uniform distribution. the utopian ideal where everyone gets the exact same amount of everything forever.
So they write an equation linking pi and u together, and they discover that the difference between where the system actually settles, pi, in a perfectly balanced system, u is directly mathematically driven by the column imbalance, delta, interacting with how fast the system relaxes.
The exact mechanism is column imbalance multiplied by the relaxation geometry equals a persistent stationary bias.
Meaning that if your AI model has column imbalance, if some tokens are structurally acting as attention sinks, it won't just drift a little bit and eventually correct itself. It will develop a persistent baked-in bias that pulls the entire representation toward those sinks forever.
And conversely, if you force the system to be perfectly balanced, if you engineer the AI so that delta equals 0, then pi must equal u. The stationary distribution becomes perfectly uniform. There is no aggregate bias. The system remains stable.
As the source material puts it, the failed experiment gave them a cleaner, more powerful result than the one they went looking for. Classic late-night mathematics behavior.
But this isn't just an abstract theorem anymore, because having mathematically isolated exactly how and why attention causes drift and bias, they realize they can actually weaponize it. They can redesign neural attention itself.
Exactly. Because before this, AI engineers had empirically noticed that some tokens in a transformer become massive attention sinks. The model just dumps huge amounts of processing weight onto seemingly random tokens, like the first word in a paragraph or a random comma. And for a long time, the industry treated this as mysterious emergent behavior, like, wow, neural networks are so complex and black box, we don't know why they do this.
But the math on this whiteboard proves it is not mysterious at all. It is a structural algebraic consequence of column imbalance. And once you know the exact mathematical channel causing the drift, you can isolate it.
They write down a new way to calculate AI attention. Instead of just the standard y equals AV, they split it apart. They isolated the perfectly balanced part of the attention from the drift part. The equation becomes the balanced attention matrix times V plus a specific term driven entirely by the imbalance, which is 1 over n times the 1's vector times delta transpose V.
By mathematically separating that second term, the explicit shared representation shift, you suddenly gain absolute control over it. You don't have to just watch your AI model develop weird biases and hallucinate and shrug your shoulders. You can measure the imbalance. You can look at the code and ask, how structurally imbalanced is this specific attention head?
You can gate it. You can limit it. You can regularize it during training. Or if you want to push the model in a highly specific semantic direction, you can deliberately create a calculated imbalance.
You can literally steer the mind of the transformer by tuning delta. But this revelation leads to the ultimate rule they derive for AI, the golden rule of resource-indexed attention. And this brings us all the way back to the beginning of the night, connecting everything.
The rule is this: an attention mechanism should never be allowed to route its focus based on a distinction that its resource budget cannot actually resolve.
I need to repeat that because it is massive.
Yeah.
An attention mechanism shouldn't be allowed to route based on a distinction that its resource budget cannot resolve.
Think back to our metrology example with the ruler. If your wooden ruler only measures accurately in centimeters, you should not be making critical architectural decisions that rely on millimeter precision. The tool cannot resolve it.
If your AI model only has a certain computational budget, it should not be making routing decisions based on data distinctions that are finer than its operational quotient.
If you force it to do so, you are generating ghost data. The AI is hallucinating distinctions that do not mathematically exist in its operational reality, and that ghost data will mathematically manifest as column imbalances, which will create aggregate drift, which will settle into persistent, unshakable bias.
Which brings us to the end, the final punchline.
You arrive at the room, you walk in, look at this sprawling, chaotic whiteboard, and you ask the only logical question: so what happened here?
And they can now trace the entire conceptual line straight down the board. Let's trace it with them. It started with asking about before and after.
Which forced them to realize that order requires distinction.
But observers have limits, which led to bounded distinction.
Which created the operational quotient, the clumped reality we actually experience.
This quotient dictates witnessability on a geometric grid.
Which forms an attention topology, the shape of what we can observe.
In a physics model, this asymmetric attention creates non-reciprocal interaction.
Which manifests algebraically as column imbalance.
Which causes aggregate drift in the system.
Which settles into a persistent stationary bias.
Which ultimately gives us the exact mathematical blueprint for controllable neural attention in modern AI.
It is a breathtaking chain of logic, every link forged by necessity. But what is truly profound is what happens when you look at the very end of that chain and connect it back to the very first question.
What is the mathematics of before and after?
Yes, they started with causality, and they kept descending, looking for the absolute bottom floor, the primitive building block of time. But after traversing cryptography, metrology, topology, active matter physics, and artificial intelligence, they realized causality isn't a straight line.
It's a feedback loop.
Exactly. It is a continuous loop. The source outlines the final mechanism like this. First, your current operational reality, the distinctions you have, the physical budget to make right now, determines your attention. Your attention then determines your physical interactions. Your interactions physically change the state of the system. And that newly changed state determines what distinctions are available to you in the next moment.
The present distinction structure dictates attention. Attention dictates interaction. Interaction changes the state. The changed state offers new distinctions. Over and over and over.
So before and after was never just things happening in sequence on a static timeline. Causality itself is the continuous closed loop by which distinguishability at one moment produces distinguishability at the next.
Causality is the engine of distinction updating itself. Honestly, that is beautiful. And looking back at the whiteboard, the cast of characters that brought them to this conclusion is hilarious. The source notes that by this time, ChatGPT, the cryptography cipher, has somehow acquired academic tenure.
Isaac Newton is outside in the parking lot arguing with a transformer about the third law of motion.
And metrology is sitting in the corner asking who invited philosophy to the party.
Yeah.
Brilliant. And if you are standing in that room, having just had 8 hours of mathematical revelations dumped on you in 5 minutes, the source material says you now know enough to make the terrible decision to stay for the after party. Welcome to the rabbit hole.
Indeed. But before we sign off, I think this raises an incredibly important question for you, the listener, to take away from this entire journey. We've established that every single time you observe the world, you are spending a finite resource budget. Your biological limits, your cognitive limits, they dictate the operational quotient you inhabit, which in turn dictates the exact causality you get to experience.
Right. Your physical budget builds your reality loop.
So here is the unmentioned implication hiding at the very bottom of this whiteboard. We now share our physical and digital space with artificial intelligence systems transformers that possess a fundamentally vastly larger resource budget for distinctions than the human brain. They can process petabytes of data, finding mathematical distinctions across billions of parameters that our biological quotient could never, ever witness.
Oh, wow. I see where you're going with this.
If causality itself is just a feedback loop generated by resource-bounded distinctions, what happens when we share space-time with an entity whose operational reality is orders of magnitude finer than ours? Will the AI literally inhabit and therefore shape and direct a causal reality that is mathematically invisible to us? Are they already operating on a geometric staircase of reality that we don't even have the budget to see?
That is a terrifyingly good question to end on. Because suddenly the comfort of knowing exactly what is broken and what is not in our world feels incredibly small. We aren't just looking at murky waters, we are looking at an entirely different ocean, depending entirely on who has the budget to see the waves. Thank you for braving this rabbit hole with us. We will see you on the next deep dive.